Hello, my name is Paula Perez. I am the product manager of CAMECA IMS-7F Auto mass spectrometer. CAMECA is, as you may know, a manufacturer of magnetic sector SIMS instruments. This talk will describe the main principles of the dynamic SIMS technique. I will show now the outline of this talk. I will start with a brief introduction to the dynamic SIMS technique, magnetic sector, SIMS instrumentation, and typical outputs. Different practical aspects of the dynamic SIMS technique will then be discussed. Choice of primary and secondary beam species, relative sensitivity for various elements, matrix effects, depth resolution and lateral resolution, depth profiling, in particular the choice of impact energy and sputtering rate, as well as the calibration method, and also the scanning ion imaging mode. I will then conclude with a summary of dynamic SIMS' main analytical characteristics. A brief introduction to the dynamic SIMS technique and instrumentation. When a solid sample is bombarded by primary ions of a few keV energy, a fraction of the particles emitted from the sample surface is ionized. Secondary ion mass spectrometry, SIMS, consists of collecting and analyzing these secondary ions with a mass spectrometer. SIMS provides a local analysis of any type of solid flat material that can be maintained under high vacuum, including insulators, semiconductors, metals, and even biological samples. Both elemental and isotopic information can be obtained for all species in the periodic table, from hydrogen to uranium and above. Dynamic SIMS is a destructive technique by its nature, and it is based on sputtering of material. It utilizes a high-dose ion bombardment that is able to erode successive layers of the sample, providing information about the elemental and isotopic composition over depths that can range from nanometers to tens of micrometers. Still the most sensitive surface analysis technique available, dynamic SIMS provides elemental detection limits that reach parts per billion for many elements. Magnetic sector mass spectrometer SIMS instruments provide the best performance for dynamic SIMS analysis. This sketch shows the operating mode of a magnetic sector SIMS instrument, the CAMECA IMS-7F Auto. In magnetic sector SIMS instruments, the secondary ions, which are characteristic of the composition of the analyzed area, are separated in a magnetic sector analyzer according to their mass. The design of CAMECA magnetic sector SIMS instruments is based on a double focusing mass spectrometer design, that is, the coupling of the magnetic sector with an electrostatic sector. This type of mass spectrometers can separate most interfering species using high mass resolution conditions while keeping a wide energy passband. It is also based on a continuous primary ion beam bombardment, as well as on a continuous secondary ion extraction DC mode. The DC mode, combined with a strong extraction field for the secondary ion collection, allows to optimize the instrumental transmission and thus to achieve low detection limits. In order to enhance the ionization yield, dynamic SIMS uses reactive primary ions, oxygen or cesium, of energy range between 100 EVs and a few tens TeVs. Some instruments work in monocollection mode, secondary ions being acquired one by one by scanning the magnetic field, as shown in this example. Other types of CAMECA magnetic sector instruments have multi-collection capabilities. Electromultiplier and/or Faraday cup detectors are available. Dynamic SIMS using magnetic sector SIMS instruments are well adapted for elemental and isotopic analysis in inorganic materials. Dynamic SIMS is ideal for depth profiling when low detection limits are required from ppm level to sub-ppb level, including for light elements, when the depth to be sampled is very large and good sensitivity is required. The sample depth can vary from few nanometers to several micrometers. For ion imaging analysis, when high mass resolution together with high sensitivity are required, and for high precision isotope ratio measurements. Analysis can be performed with high throughput and productivity. These capabilities have ensured its regular use in fields such as microelectronics, for dopant depth profiling in silicon, for example, as we can see in the left figure. For biology, in the middle we can see an example of uranium intracellular distribution map. And for geology, for high precision isotope ratio analysis, on the right figure one can see the oxygen isotope mass spectrum. Dynamic SIMS in practice. The choice of primary and secondary beam species and polarity is made simultaneously. Oxygen primary ions are generally used to investigate electropositive elements, boron, metals, alkalis, as they enhance the ionization of positive secondary ions. Positive oxygen ions are more common, but negative oxygen ions are preferred when bulk insulator samples are to be analyzed, as they minimize the charge buildup during sputtering of insulating materials. Cesium primary ions are generally used to investigate electronegative elements, carbon, oxygen, phosphorus, sulfur, as well as for semi-quantification of matrix species using the MCS plus cluster technique. We will come back to this topic later on. The typical choice of the primary ions for the different elements of the periodic table is shown here. Oxygen primary ion bombardment enhances the ionization yield of electropositive species in blue, while the cesium ion bombardment enhances the ionization yield of electronegative species in red. Note though that a few elements in yellow are not so sensitive with dynamic SIMS, such as mercury, zinc, cadmium, and noble gases. For such species, the choice of primary ions is less clear. The ion yield may be increased by measuring a cluster ion, combination of the species of interest with a matrix species, typically in negative mode. To be pointed out that the MCS plus technique may also be of interest for species with low ion yield. For example, studies have shown that the best sensitivity for species such as zinc, nitrogen, or helium is obtained by measuring the MCS plus molecular ion. The SIMS ionization efficiency is called ion yield, defined as the fraction of sputtered atoms that become ionized. We can see here the relative sensitivity of trace elements in silicon matrix for cesium bombardment conditions in blue and for oxygen in red. It shows that the ion yield varies over many orders of magnitude for the various elements. Quantification of dynamic SIMS data, converting secondary ion signal intensities to absolute concentrations, can be sometimes delicate because of matrix effects. The fraction of particles emitted from the sample surface that are ionized and sent to the mass spectrometer is highly dependent on many instrumental factors, but also depends on the surrounding chemical environment, hence varies with the chemical composition of the matrix. These are known as matrix effects and mean that for the same concentration of a given element, its signal in a silicon matrix may be different from its measured signal in a different matrix. Note that the sputtering yield, sputtered atom per incident primary ion, also varies with the sample matrix composition. So for a multi-layered sample, the sputtering rate is expected to be different for each layer. Data quantification requires standard samples with a known concentration of the elements of interest and same matrix as the sample being studied. One very effective semi-quantitative dynamic SIMS methodology to tackle matrix effects is analyzing MCS plus or MCS2 plus ions. The mechanism is indeed a kind of post-ionization by recombination of the sputtered neutrals by the sputtered cesium ions. so minimum ionization influence by the matrix. Dynamic SIMS offers both depth resolution and lateral resolution that allows for depth profiling and surface imaging within a sample. The detection limit is determined by the number of atoms available in the analyzed volume. One needs to integrate the signal from a sufficiently large volume in order to have enough ions reaching the detectors. This allows to have good statistics, good precision, and low detection limits. Therefore, for a given detection limit, a compromise between lateral and depth resolution must be decided. If one wants to optimize the depth resolution, that is, to erode the sample thin layer by thin layer, typically during depth profiling, one needs to integrate the signal over a large sample area. If instead one wants to optimize the lateral resolution, typically during ion imaging analysis, one needs to integrate the signal over a large depth range. During SIMS sputtering and ionization process, the incident primary ions implant into the surface layers of the sample and trigger a cascade of atomic collisions, causing the local ejection of atoms and clusters of atoms from the surface. The depth resolution is limited by this collision cascade, target atoms mixing during ion bombardment, and may also be limited by roughening effect, non-flat bottom crater, that may occur for some type of material. Metal or polycrystalline samples are typical examples, and for given analytical conditions. Because SIMS process is based on target atoms mixing, the physical limit of the depth resolution is around 0.5 to 1 nanometer. In general, high depth resolution requires using low impact energy and convenient primary beam incidence angles. The depth resolution is the width of an interface as measured by depth profiling. It can be obtained from a measurement through a steep interface, and it is usually expressed in nanometer per decade. Depending on the instrumentation and selected analytical conditions, primary impact energy in particular, the depth resolution varies from sub-nanometer to few tenths of nanometers. To be noted that the depth resolution is different from the depth definition, which corresponds to the data point density, number of data points per depth unit. Dynamic SIMS is often used for elemental and isotopic depth profiling, which provides the distribution of species versus depth in the sample. The secondary ion intensity is recorded over time in the detection system, electromultiplier or Faraday cap detector, for selected species, whilst the sample is eroded by the primary beam. During sputtering, the primary beam is rastered or scanned over a specific area of the sample, creating a flat bottom crater. The secondary ion signal is collected only from the center of the crater. Crater edges are excluded thanks to an electronic and/or optical gating, optimizing the dynamic range of depth profiles. As we can see in this example, with appropriate analytical conditions, the dynamic range of a depth profile can span over up to 6 decades of concentration range. Depth profiling, high versus low impact energy. High impact energy is selected for fast analysis when large depth range is to be analyzed. The large analyzed volume, by combining high impact energy and large analyzed area, increases the statistics of detected ions and enables higher dynamic range, so lower detection limits. Lower impact energy is used for optimized depth resolution by minimizing the thickness of the ion mixing region, and also for improving near-surface and interface quantification by shortening the sputtering transient regime. Note that neutral oxygen leak combined with oxygen ion bombardment may also be used for this purpose. The sputtering rate determines the analysis time for the depth profile. It depends on the sputtering yield, number of sputtered atoms per incident ion, that is a function of energy, incidence angle, and mass of the bombarding species, and which also greatly depends on the sample composition. For given analytical conditions, the sputtering rate is then varied by changing the primary beam current and/or raster size. A high sputtering rate reduces the analysis time and the relative contribution from the vacuum. However, one must also consider data point density of the profile. If the sputtering rate is too high, depth information may be lost, especially at interfaces. Depth profiling raw data show the measured intensity or count rate for selected species versus the analysis time. How to obtain quantified data, concentration versus depth. Depth calibration, conversion of sputter time to depth, is usually carried out by measuring the final crater depth with a mechanical stylus profilometer, or by measuring the sputtering rate on a standard sample using the known depth or thickness value. The concentration calibration, conversion of count rate to concentration, requires a standard sample with same matrix composition measured using the same instrumental settings. From the depth profile on the standard sample, an RSF is calculated from the known implanted dose or bulk concentration. This RSF, relative sensitivity factor, is applied to the depth profile on the unknown sample to quantify the signal of the species of interest. For the ion implanted samples, the integral of the quantified depth profile provides the implanted dose value. To perform imaging, the spatial position of each secondary ion must be mapped to the sample surface. In the ion microprobe imaging mode, the primary beam is rastered across the surface and the signal is detected pixel by pixel. The lateral resolution is determined by the primary beam size. Therefore, the SIMS lateral resolution is limited by the beam diameter and by the collision cascades, target atoms mixing, with a physical limit of the lateral resolution being around 10 to 20 nanometers. High lateral resolution requires highly focused primary beam. Ion imaging analyses are typically performed at high impact energy because the beam focusing improves with increased ion source voltage. I will now conclude with a summary of dynamic SIMS' main analytical characteristics. SIMS is the most sensitive elemental and isotopic surface analysis technique. Dynamic SIMS is a destructive technique by nature. This is not an issue when enough sample material is available, but may be critical for small or unique samples, particles or nano-objects. Hence, when rare or ultra-small samples are analyzed by different techniques, dynamic SIMS should be the last analysis in the sequence. Quasi all elements in the periodic table can be detected, from light elements to uranium and above. Dynamic SIMS provides in situ localized elemental composition. It can be used for depth profiling with excellent depth resolution down to sub-nanometer, depending on instrumentation and analytical conditions. For imaging analysis, dynamic SIMS lateral resolution is limited by the primary ion beam diameter, smaller than 1 micrometer down to 50 nanometers, depending also on the instrumentation and analytical conditions. It is also possible to obtain 3D volume reconstruction from ion image stacks recorded sequentially while sputtering in depth. As already said, dynamic SIMS provides very high sensitivity with detection limits down to ppb in depth profiling mode and in the ppm range in imaging mode. SIMS quantification is reliable and simple for low concentrations, below 1 atomic percent, provided the standard is available with the same matrix composition. For higher concentration, calibration curves are necessary. Direct semi-quantitation is possible in some cases using MCS plus cluster technique. Dynamic SIMS has the additional capability to measure very precise in situ isotopic ratios. It can be applied to any solid material that can be maintained under high vacuum, conductive, semiconductive, and also insulating samples. Sample preparation for dynamic SIMS is crucial for obtaining reliable results, but fortunately it tends to be relatively simple. For solid materials, SIMS requires a flat, polished sample surface. If you have any questions, please do not hesitate to contact me at this email address. Thank you so much for your attention.